All right, so this work is about implementing 2 product recommender systems on Alibaba. Okay, so if you don't know what assortment optimization is, that's okay. Just think product recommendation systems, and I'll kind of formally define it later on. Okay, so as this talk progresses, I'll first paint kind of a picture of where exactly we implement these 2 product recommender systems on Alibaba. So I'll show you the exact setting where we do that. And then I'll talk high-level details about the 2 approaches. Talk about their upsides and downsides, talk about how we implemented them, things like that. And then I'll finish with the results of a week-long field experiment where we actually tested these 2 approaches on real customers. Okay, so both of these approaches can be broken down into 2 phases. Okay, an estimation phase, a predictive phase, and an optimization phase, a prescriptive phase. And really kind of the distinguishing factor of these 2 approaches is how they handle the estimation phase. Okay, so on the one hand, we're going to have a machine learning-based approach. And this is Alibaba's current approach. And on the other hand, we're going to kind of ironically have kind of a new way to look at product recommender systems using kind of classic techniques. So in the second approach, we're going to use classic models from economics, marketing, and operations, specifically customer choice models. And we're going to adopt the multinomial Logit choice model, or the MNL choice model. If you're not familiar with that, I'll define it later on. So we're going to use that in the estimation phase. And then we're going to solve what's called assortment problems in the optimization phase. And kind of at an even higher level, the prescriptive kind of message of our work is that machine learning algorithms are very good for prediction. Right? So if you want to solve a prediction problem, machine learning is great. But when these predictions seed subsequent optimization problems that guide key operational decisions, you have to be careful. The 2 problems can be linked. Because now there's 2 phases. You have to do very good at estimation, and you have to solve a sophisticated optimization problem to guide your decisions. So we'll see that trade-off here with the 2 approaches. Okay, the machine learning is going to be very good at estimation, but then we're kind of handcuffed. And we're going to see that we can't really solve a sophisticated optimization problem. And I'll formalize that later on. While the MNL model is not as good at estimation, but we solve kind of what turns out to be a more nuanced optimization problem. Okay, and I'll talk about those trade-offs as I progress. But first, let me tell you about the exact setting that we study. Here I have a video of that exact setting. I'm going to kind of give you the play-by-play as I start the video. Okay, so we're looking at 2 of Alibaba's online marketplaces, Taobao and Tmall. And they connect third-party sellers to consumers. Okay, so here we're on the front page of, I believe, Tmall. And each of these sellers has their own seller page on the mobile application. So here, I'll be searching for a ramen seller. Okay, and when you come to the front page of any seller, you're presented with a coupon. So in a second, you're going to see 3 coupons appear right here. And you can click one of these 3 coupons. Here's 3, 5, and 10 RMB. And you're presented with 6 product displays. And so you can use this coupon, here a 5 RMB coupon, on any one of these 6 products. Okay, so the recommender system we're focusing on, and the 2 approaches we're going to actually implement, are on deciding which 6 products to show for each customer who claims one of these coupons. Okay? So to give you a sense of the scale of the problem, okay, we're dealing with about 250,000 active sellers. And the products they sell can be partitioned into 3 categories: snacks, clothes, and electronics. And here's kind of the order of magnitude of the products that each of these sellers kind of deals with. Right? So even with just 100 products, how many 6 products displays are there? Right? There's 100 choose 6, which is over 1 billion. Right? So the optimization phase is certainly non-trivial. We see about 4 million customers per day of traffic. And within each day, there's about $3.1 million kind of influenced. Right? So our week-long field experiment is going to influence over $20 million. OK, so let's jump into the 2 approaches. But before I do that, I'm going to kind of come back and forth to this kind of dummy setting just to kind of illustrate some of the points. OK, so let's pretend you're Best Buy. You have 3 different slots on your website to show TVs. OK, this capital N here will be the set indexing the products I could potentially offer. Here I just have 5. And there'll be a revenue associated with each TV. Right? So RI is the money I make if I sell 1 unit of that product. And each of these TVs obviously kind of has different features, right? Different sizes. Are they smart TVs? Are they HD, etc. So at a high level, here's the question we're considering. For each customer that arrives, which 3 products, or in Alibaba's case, which 6 products, should I show to maximize my revenue? And I bolded each customer here because we're going to show personalized assortments, right? So for each customer that comes in, we're going to see the product features, we're going to see customer-specific features, and we're going to come up with a personalized assortment. And so what that means is we have to solve this optimization problem online, right? So for every customer that comes in, right, we have to be able to solve this problem efficiently to determine the 6 products to offer. Okay, and I'll kind of give you I'll tell you exactly how fast we need to solve it as I progress through. Okay, so now the first approach, the machine learning approach. And unfortunately, I can't give you the full details of the machine learning algorithm. But on the next slide, I'll show you a case study that kind of illuminates some of our main kind of qualitative point with regards to the machine learning approach. So what does this machine learning approach do? It takes a bunch of product features, a bunch of customer features, and it puts them into, I'm just going to call it the machine learning black box. Again, I'll give this black box some transparency on the next slide when I kind of talk about this case study. And as output, we get purchase probabilities. Okay, these purchase probabilities, so PI is just probability the customer buys product I. Right, so P1 probability buys product 1, P2 probability she buys product 2, etc. Right, these should really have a customer index because they're personalized. Right, so for every customer, there's going to be a new set of purchase probabilities that our machine learning black box spits out. Okay, so just to kind of illuminate the machine learning a little bit, we have this case study here. And our kind of qualitative main point is that machine learning is way better at prediction. So our kind of main theme, I'll show you it here, I'll show you it later in our actual field experiments, is that the machine learning algorithm does a lot better in prediction. So here we have the top 10 sellers on Tmall, and we have 2 weeks of historical data. Okay, so you can see this 2 weeks of historical data are non-trivial amounts of customers. Okay, and I haven't told you what the MNL model is, but for now, take that also as a black box. So we fit out-of-the-box gradient-boosted decision trees. Just kind of out of the box, we use cat boost specifically, but we don't do any sort of hyperparameter tuning, nothing like that. And then we fit MNL models. And here's the results. So we assess the accuracy on out of sample data sets on 2 metrics. The first is kind of your classic classification accuracy. So here, higher numbers are better. Right? This is for every customer. We have 6 predicted purchase probabilities. This is just the fraction of time that the item purchased is our highest predicted purchase probability. Okay? And here you see huge improvements over MNL, anywhere from 10 to 100%. The second metric we use is kind of a natural extension of classification accuracy. We call it average rank. So here what we do is we take our 6 estimates for the purchase probabilities, we sort them in decreasing order, and we look at the rank of the item that was actually purchased. Right? So if the highest estimated purchase probability was purchased, we give that a rank of 1. If the second highest was purchased, we give it a rank of 2. We take that average over every customer arrival in our testing set, and that's what we report. So in this case, lower is better. Lower is better. And you can see, again, we see huge improvements. So the idea, the take-home message from here is machine learning is better at prediction. But does higher prediction accuracy always guarantee we'll show more profitable assortments? Okay, that's kind of the high-level question we're thinking about. Okay, so once we have before I answer that question, let me kind of talk about the optimization side. So once we have those estimates, we need to solve an optimization problem. Okay, so here's that optimization problem. I need to choose a subset of products to offer. I need to choose exactly 3. Again, in Alibaba's case, this is 6. And I need to do it to maximize my expected revenue. Right? For any fixed assortment, that's a sum over the products I offer, the revenue of each product times the purchase probability. And so this optimization problem here is trivial. Right? All we do is we sort by the RIs times PIs and pick the top 3. So this is both kind of the nature of this optimization problem is both a kind of a pro and a con. It's a pro because, as I mentioned, we need to do this optimization problem online. So we need to solve things in 50 milliseconds. Right? That's kind of the threshold to prevent any sort of lag. And I'll explain a little later on the next slide why it's a con. Okay, so that's the machine learning-based approach. Let me kind of give you high-level pros and cons. Pros, powerful machinery to do estimation. Okay, we saw the estimates are a lot more accurate than the MNL model. And we have a simple accompanying optimization problem. Right, we need to solve in 50 milliseconds. All we have to do is sort So we can do that very efficiently, obviously, and pick the top 6. What are the cons? We don't account for substitution behavior. So what I mean by this, and where this manifests itself, is that these estimates of the purchase probabilities are not a function of the assortment I offer. So if I offer product 1 with 2 and 3, products 2 and 3, versus offering product 1 with 4 and 5, my estimate of P1 does not change. Does not change. OK? And so what we'll see is that the MNL model and more kind of generally customer choice models are built to capture substitution behavior. OK? They're kind of created for that purpose. The question is, does accounting for this actually make a difference when we decide what products to offer? And the second thing is the interpretability. Right? This machine learning is really, at the end of the day, most machine learning algorithms are kind of black boxes, at least to some degree. And if we wanted to, for example, solve a pricing problem, the machine learning algorithm does not give us a parametric relationship between price and purchase probabilities. So we can't even formulate a pricing problem. Whereas the MNL model gives us a very nice relationship, as you'll see, and people formulate these and study them. OK? There are many papers about how to do pricing under the MNL model. OK. So what's kind of the high-level question? Right? Can we do better than this machine learning approach by using customer choice models to model demand, and then by solving assortment problems to find what to offer? So what is the MNL model? So we're using the MNL model to model demand. The MNL model is perhaps the most popular and well-studied choice model out there. And it falls under this category of random utility maximization choice models. So under this broad class of choice models, customers associate random utilities with each of the products, and then purchase the product with the highest utility. Under the MNL model, we can break this random utility. So UIT is the random utility customer T associates with product I, into a deterministic component and a random IID Gumbel error. The Gumbel error is what makes things what gives you the MNL structure. And then we can write this deterministic component as a dot product between a beta coefficient vector and a feature vector. So you can think of XIT as being all my customer and product features. And then when you compute these probabilities, so kind of given this structure, PIT of S is the probability product I is purchased by customer T, given I offer assortment S. Right? That's exactly the probability that product I has the highest random utility. And when you do the calculus, you get these very nice kind of rational expressions. OK? A lot of times, you'll see these exponentiated beta times feature vectors written as VITs and referred to as preference weights. Right? So here, the purchase probability is proportional to the preference weight, but then we normalize by the sum of all the offered preference weights. This one here is a normalized, what we call no purchase option. It's a dummy product that's always offered, and it represents the option for the customer to leave the store without making a purchase. So what we're estimating is these betas. So when we estimate the MNL model, we're estimating these betas, and we do it just by MLE. So it's well known that the log likelihood under the MNL model is concave. OK? But kind of the underlying question here is, can we solve this MLE problem at this scale? So when we have 40 or 50 million customers. So for each customer, we know what we offered. We know what 6 product assortment we showed. We know what was purchased, and we know all their features. Right? So here's just the likelihood of a single event. Right? It's just the purchase probability. And the MLE problem is as follows. Again, we actually just solve the log likelihood. So log likelihood is convex, not the likelihood. And we solve the log likelihood by a custom TensorFlow implementation. OK? And both machine learning model and the MNL model, we fit the data on a 2-week rolling horizon. OK, so there's tens of millions of data points. So this tau is in the tens of millions when we solve these MLE problems. For features, OK, we're going to use 25 features. 25 is somewhat arbitrary. We'd probably see the same results with 20 features or 22. But we're using the 25 features that have the highest importance scores from the machine learning-based algorithms. OK, and I'll show you actually that using 25 versus the full featured model that I'll talk about a little later doesn't have much of a difference in terms of predictive accuracy. OK? OK, so we fit the MNL model. We solve the log likelihood problem. We get the beta coefficients. Now, for any customer, I can compute these purchase probabilities. Now I have to solve the optimization problem. This problem is non-trivial. Why is it non-trivial? Because now my purchase probabilities depend on the assortment I offer. So as I change the assortment, my purchase probabilities change. So I can't just do a sorting. So in the literature, there are 2 papers that show how to solve this cardinality-constrained assortment problem. The first is an LP-based approach. The second is a purely combinatorial approach. And we kind of take this combinatorial approach and shave a log n factor off of it. Right? Every millisecond counts. And we find that we can implement this order n squared algorithm within the 50 millisecond threshold. OK, so what are the pros of the MNL-based approach? Right? Instead of using kind of these general machine learning tools that are built as kind of general tools for prediction, we're using the MNL model, which is specifically built to capture customer purchasing behavior. So it's grounded in theory, in economic theory, and our estimates of the purchase probabilities incorporate substitution. So now when we solve the optimization problem, we're seemingly solving a more sophisticated problem. The cons are harder to incorporate click behavior. So the estimates in the machine learning model, I kind of glossed over this. Those P's, we get those P's by actually first estimating click probabilities, and then conditioned on click, we estimate a purchase probability. And we use machine learning for both. For the MNL-based approach, we're completely ignoring click probabilities. We actually just wrote a paper to deal with that, but it's kind of theoretical in nature. And we've assumed here a linear kind of structure with the utility. So that's kind of another downside. OK, so let me actually get to the results. So we have 3 buckets. We test the full feature MNL with the top 25 features. Again, 25 is arbitrary. We probably see the same results with 20 or 22 features. And we test the MNL with top 25 features. And then we test the machine learning-based approach with all features. Right? So actually, in the current implementation, Alibaba uses hundreds of features. But we'll see going from 25 to 100 actually doesn't make that much of a difference in terms of prediction accuracy. OK, so here's the data for the field experiments, the week-long field experiments. Number of sellers, number of customers who were shown, number of customers who were actually within our field experiments. Here's how many items were purchased, and here's how much money we influenced. And just as a quick randomization check, here are the kind of the demographics of the 3 buckets. Right? And we can see they're very similar. So it looks like we have a properly randomized field experiment here. OK, now for the results. First, prediction accuracy. Right? So here we fit our models, and we look at out-of-sample prediction accuracy. Here I'm only going to show you classification accuracy. So here we see the MNL model getting crushed by the 2 ML models. Right? So here's ML with 25 features. Here's ML with all the features. And as I mentioned, we don't see that much of an improvement. The top 25 features are descriptive enough to get us most of the way. But then the underlying question is, does more accurate predictions guarantee that we're going to show more profitable assortments? And as I said, or as I don't think I said, the answer is no. Right? So here's the revenue per customer. Right? So the MNL gives us a 28% improvement over the apples-to-apples 25 feature comparison, and even does a little better than the full feature. Even does a little better than the full feature. So that one's not statistically significant. But here, with the apples to apples, we see a 28% improvement, which is equivalent to $6 million per week. So why did the MNL do better? So one thing we can tell you is that it seemed like solving the more sophisticated assortment problem actually mattered. So here's the average price of an item purchased under each of the approaches. So we can see under the MNL approach, it's about 5% higher. So we're kind of just recommending better assortments. People are buying more expensive items that give us more revenue. So the natural question is, did we test full feature MNL against full feature machine learning? And we have preliminary results for that. I can only share with you 3 days of that. And we see gains. Right? So we see here's full featured machine learning against full featured MNL. And just over these 3 days, we see a 2% improvement, which is close to a 30% per year. They didn't give us visit level data for this, so I can't give you the accuracy numbers. So I can't give you accuracy side by side with revenue performance. Actually, we just analyzed this over 5 days. They gave us another 2 days of results, and the results were actually over 3%. Okay, so we still see a substantial improvement when we do the MNL with the full features and the ML with all the features.